Okay, welcome to the last lecture of the quarter for CS 110. Don't clap too loudly, being the last lecture. I hope you guys have enjoyed the course as it goes. We have one other big thing, which is your final exam, which is next Friday, a week from Friday, at 8:30 in what is it? It's in which auditorium is it? I want to say it's Hewlett 200. I think it's Hewlett 200. It should be on the website anyway. I'll confirm that and make sure that it's correct. Somebody just asked about if there's going to be a review session. I think there will be. I haven't talked to the CAs about that yet, but we'll have some review session. If the CA doesn't want to do it, I'll do it, and we'll make it work out. But the CAs normally do a final review session. And then we will have grades for all the assignments up to the final assignment before the end of either the end of the weekend or Monday, Tuesday. So you'll be able to check that. We hopefully will have assignment 8's grade by like midweek next week. So you should have all your grades before the final exam, and then we'll go with that. If you have accommodations for the exam and you don't hear from me before like Monday or Tuesday next week, please shoot me an email. And otherwise, do post on Piazza if you have questions about the final and so forth. All right. The only other thing for the final exam, I'll probably post last quarter's Blue Book final. So if you want a final to practice on with Blue Book, you can use that. All right. Any questions before we get going? All right. So I was talking to Phil about what the last lecture should look like. And he made a very good suggestion, which is kind of a fun one. He said, hey, why don't you talk about systems today? And like, what is kind of the latest thing going on in systems that some of you might be interested in? Who here has taken an AI class or plans on taking an AI class here? Yeah, most people here, right? Whether or not you're like a CS major concentrating in AI or not, probably not a terrible idea to take an AI class or a machine learning class, just because you'll see a lot of it in the next couple decades as you kind of launch into your own careers. AI and machine learning it's not going to get any smaller, at least as far as I can tell. I think we've hit that kind of critical point where AI is just going to keep getting bigger and bigger, although I'll have comments about when people thought that in the past as well. So we thought we'd talk about systems today. In particular, we wanted to kind of talk about, I picked out a whole bunch of these, many of these were Phil's suggestions, to kind of go down a little bit into, hey, what are the systems needs and where do systems play a role in some of these things that you've probably either used before or may use or have at least seen or heard of before. In particular, I wanted to just talk a little bit about the mainstream industry use of Linux. How many people have Linux installed on your computer right now? Like actually more than, well, this is 110, maybe not more than I might expect, but probably, maybe 10% of you or so. In industry, you will probably see much more Linux than you have up to this point. Now, if you've done internships and stuff, you might have already used Linux. And of course, we use it in Myth machines and so forth. So we'll talk a little bit about that. And then we'll talk about a couple of things that are happening at Google, and then a couple of things that are happening at Amazon related to artificial intelligence and then storage and things. And we'll talk about how how systems plays a role there. And then I thought it'd be interesting to just chat for a minute about the internet backbone. We've talked about networking and so forth, and have you ever thought about like, hey, where is this data flowing when it has to get from here to wherever else? We've seen you can actually figure this out by running. Why am I blank? Traceroute. I don't know why I blanked on that. By running Traceroute, you can actually see all the various hops. But the question is like, who owns some of these hops and where are they getting and who's paying for them and so forth. And I wanted to talk about that for a few minutes. And then finally, I wanted to just end up with talking about some systems programming for like entertainment, right? Like what kind of systems has happened recently or in the near past anyway for systems. So we can talk about a little bit of that. I don't have tons of details on all these things, but feel free to ask questions. And if I can't answer them, Phil may have some comments on those as well. Okay, so that's what we kind of end the quarter with. Mainstream industry use of Linux. So we've used Linux in class. Some of you have Linux installed on your computers. I've had Linux. I think only once I've ever owned a computer where the main operating system was Linux. I've run Linux in many, that's not true. I've got a server that does, but many of my computers, I'll run Linux in a virtual machine. And one of the nice things about Linux is it actually, especially depending on which version of the Linux you get, it doesn't necessarily take up that many resources. So running it in a virtual machine is actually very doable. Whereas sometimes other operating systems like Windows kind of bogs your system down a little. Never found that to be the case with Linux. So you can do that. Most of you will go to companies where Linux is a kind of a staple and kind of the main thing that is used for the back end in particular, particularly the servers, and in many cases the front end and so forth as well. Although a lot of big tech companies you'll go to, they'll give you the option of saying, hey, what do you want your laptop's operating system to be? Microsoft, Windows, or Mac, or Linux, or whatever. You can choose that. The odds are very good that the servers you'll be interfacing with are going to be Linux servers. There are many Windows servers as well, but Linux seems to have kind of taken that space and really is the kind of default operating system for a server. Okay, and why is that the case? Well, I think there's a number of reasons. Number one, it's free. That's probably the biggest one. You don't have to go and pay a company for their proprietary software, namely, let's say Microsoft, for their servers, and you don't have to buy into that. Although many companies will pay a company like Red Hat to manage the software for their servers. They are not buying the software, they're buying the support for the software. And that's an important part of it. And trust me, Red Hat and those kinds of companies have lots and lots of systems programmers who are contributing to the Linux kernel and to a lot of that other software as well. So it's free in that sense, although most companies will either have in-house people who they're paying to keep the software up, or they'll be paying somebody else to do that. But they're not paying for the software itself. It's open source. That's a huge thing for some companies where you really want to you need the hooks into the low-level machinery of your operating system if you're going to do something that needs it, right? If you have device drivers that need to interface at a really low level, for your hardware, or your own proprietary hardware, or some software you're designing, you're going to want an open system where you can dig in and actually grab those hooks. And that's not necessarily true in a lot of other operating systems. That's another reason you might use that. The other one is Linux computers are very good at the networking stack, and if you have a bigger company and you start building data centers, it's much easier to drop in 1,000 Linux computers than it would be to, let's say, try to go and get other servers. Although, again, companies like Microsoft do try to make it relatively easy for you to do that. So you will see lots of Linux as you go through the rest of your careers, almost certainly in some form or another, okay, if you're going to stay in that. Okay, let's talk about hardware for a minute, okay? The graph up here, it's a little bit small. I'll bump this up. In particular, I'm going to start by talking about hardware as it relates to artificial intelligence. So artificial intelligence has been around a while. It's been around since the 1950s, and it is the Lisp programming language was actually basically developed by John McCarthy, who ended up being a professor here. He started at MIT, ended up here. And it was basically, the idea was, hey, here's a programming language that we can use for artificial intelligence. And the people in the 1950s were still trying to figure out what kinds of things could computers do and solve in an artificial intelligence sense and a machine learning sense. And there was a lot of hype about it. And that hype lasted until about the mid-70s, when it turns out that people went, wait, you've been telling us about all these great AI things, and they don't seem to be happening, so let's focus our attention elsewhere. And then so we got a dip in like how many people were thinking about and doing research in AI. And then that happened again where it started to climb up again. And then in the mid 80s, we had another kind of downturn in AI. And we called these the AI winter, as it goes, because it was a time where people weren't really doing that much AI research. And there were a lot of good ideas, but they weren't coming to fruition, and people were getting frustrated and kind of going into other places. And then, of course, after this drop, there has been another explosive growth in AI since then. And what are the reasons for some of these AI winters? Well, part of it is that the hardware had not quite caught up to the algorithmic needs of AI. Okay, and so you got to this point where people said, well, we've got all these great ideas about how these computers can do it, and they try to go and program these things, and it's just not fast enough to do anything in a time that will be worthwhile. Okay, or the memory there isn't enough memory to handle the types of things you're trying to do, and so forth. So I'll argue that is part of the reason you get these dips, is that the hardware hadn't quite caught up. And now we're to a point where the hardware is in a state where we have the ability to do all these things like neural networks and other machine learning algorithms, and that's why we're seeing a lot of this explosive growth. Okay, so that's the kind of the preface to like, where is hardware today? Okay, and kind of framing it from an AI perspective. So.
I think the one other thing which really changed was the internet. Before that, people never had enough data to do really deep, really strong machine learning. Like you want to learn how to recognize voices. What do you record people? And it's thousands and tens of thousands of hours in a recording studio. Versus, everybody's talking to their phone, right? And now, then it's easy to get all the data that you need.
Yeah, that's a very good point. That the network. Did anyone ever use? Is it Google 411? I think that was a thing about 10 years ago. It was literally, you could go and you dial a number, and it would be Google doing some. They'd have an operator, and you could find out about things and whatever. The reason they set that up, the main reason they set that up, was not to be like, hey, we've got this cool you can find out information. It was to record your voices. Like that was literally, they wanted millions and millions of people's voices to record what they were saying so that they could do processing on it to do artificial intelligence. So yeah, I think Phil's point is well taken, that the internet and the kind of rise of the ability to collect a lot of data was another huge part of it. So, but let's focus on hardware for a minute. Who's heard of Moore's Law? Most everybody? Okay, some people have not. Moore's Law was kind of this statement by Gordon Moore, and Gordon Moore has two buildings over, by the way, on this campus. He was a founder at Fairchild Electronics, and then was I think, CEO or maybe a founder of Intel as well. Yeah, so he was kind of big in the field of electronics, and he, in a paper in 1965, he made this kind of comment about it looks like computer chips or microprocessors are going to, the number of components on those microprocessors is going to roughly double every year. Okay, and he said because of the way technology is scaling down, and we're getting better materials science, and we're getting better at engineering these chips, it looks like roughly every year we will double the number of components on an integrated circuit. A chip, basically. And if you can make a translation from that to processor performance, like things will speed up because you can put more transistors and so forth on a chip. Things are smaller, they're closer together, they're just faster in general. And it turns out this has been a remarkably good prediction of how computers have increased in performance over the years. Okay, so if you look at this graph, and keep in mind this is a log graph, so the performance versus a computer in the 1970s called the VAX 11780, computing performance has increased exponentially since then. Okay, but it hasn't been perfect, and it certainly hasn't been perfect in the last decade or so. Okay, there is another guy named Robert Dennard who was at IBM, and he recognized that yes, you will have smaller transistors, and as you have smaller transistors, they actually take less energy to work, and so therefore you can actually keep what we call the energy density on a chip roughly the same as well. So you're sticking more stuff and you're doing more work on a particular chip, but the amount of energy you spend to do all that extra work is staying roughly the same. And he made that prediction in about 1974 and said this is going to be what happens. And it was relatively true until about a decade ago, or a decade and a half, actually, right at the turn of the century. I like saying that. The turn of the century. This kind of people started going, oh, this is something's going on here. We actually are putting more transistors on the chip, and because of the fact that we're cramming so many on there, our chips are heating up more, is really what it is. And so you can't necessarily make them faster, and you can't cram as many smaller components on there because you run out of the ability to cool your chip. And it's rare that people want to cool their chips with anything else than a piece of metal as a heat sink or fans or so forth, although we'll see an example later where that's not the case. But it was just getting impossible to do that. So we've hit kind of this area where chip performance is not necessarily getting better, although it's had a great run. So the supercomputer in your pocket is millions of times faster and has millions of times better performance than computers from the early 1980s, simply because of these so-called laws that have come to be. But we're getting to a point where that's not the case. So what have chip designers done? Well, in the early 2000s, they started switching their kind of consumer processor model from a single core, very fast processor to multiple cores. And we've talked about this in class lots of times. So about 2005, 2006, you could go start buying a computer for regular computer prices. You could still buy multi-processor computers before this. But around 2005, 2006, you could start to buy multi-core, 2, 4, 8, etc. core computers that helped with the energy problem, because you would have each processor, you could fit more processors on a chip because you're still getting smaller, and you could deal with the energy a little bit nicer too. And you've kind of found out that this leads to challenges of, how do I effectively use all these cores, right? All this stuff we've talked about with concurrent programming all of a sudden becomes a reality when you have more than one processor. Before this, it was you got one processor, you just have to run with it. And now you've got multiple processors. How do they interact with each other? How does the memory system work related to these processors? How do you keep things coherent as far as two processors dealing with one with memory and so forth? There's another little law in here that I looked up called Wirt's law, which is about that software is getting slower more rapidly than hardware is becoming faster. There's a fun paper to read about this related to Microsoft Office, where Microsoft Office just keeps having more and more bloat because they realize they can get away with it. Like if you tried to run today's Microsoft Office on a computer from 1996, it wouldn't even, obviously it wouldn't run because the operating system and so forth have changed. But if you could get it to run, it would be dog slow because of the fact that it's just so much more bloated. And there's more features and there's lots of other good things about it, but it's more bloated. And because of the fact that processors have gotten so much faster and memory has gotten so much cheaper, programmers haven't necessarily had to worry about being so efficient in their coding and so forth, because hey, we get all this extra performance for free, and so we might as well use it. So there's a fun paper to read about that. It's called I forget what the paper's called, but the term is the Great Moore's Law compensator. In other words, people keep writing slower programs because they can, and it's actually worse than the speed up you're getting from that. But at this point, now we have CPUs that had 2, 4, 8, many cores, and we had all these systems challenges to use them. Operating systems needed to change, and even user programs needed to change if you wanted to utilize those. Okay, well, what was another solution to some of these issues? And by the way, you kind of capped out at about 4, 8, 16, maybe 32. Some of the higher end processors might have had 64 or 128 cores, but then we were getting into this is not like something that the average person is going to buy. What happened? Well, one thing that happened was GPUs kind of came along. And graphics processors, so your computer has both a CPU and also has a GPU in it. And depending on what brand you have and if it's a desktop or a laptop or whatever, you may have a more or less powerful GPU. But GPU companies like NVIDIA and AMD came along, and they were trying to solve the problem of we've got lots and lots of pixels, and we've got lots and lots of things we want to do with those pixels on the screen. And in particular, it's a two-dimensional problem, right? And then all of a sudden it's 3 dimensions if you start thinking about the 3D nature of images and so forth. And these things don't scale very well. If you took CS106B or algorithms, n-squared behavior is not very nice. We kind of hate n-squared, and we certainly hate n-cubed behavior, right? So what did they figure out? Well, these GPU companies came and they said, well, we can actually realize that pixels in many ways are independent of each other. A pixel on one bottom left side of the corner, bottom left and top right side of the screen probably don't have that much interaction with each other, although if you're shading things and you're lighting things, and that's not necessarily true. But it's a very parallelizable problem where you've got lots of pixels and you can deal with them relatively independently, or at least in a pipeline where you can do a computation on a particular pixel that doesn't necessarily directly need input about other pixels. So you can do them in parallel. And so what they did was they said, well, let's create a processor that has not 4 or 8 or 16 cores, but hundreds and then nowadays thousands of less powerful cores that do some things very, very well. And so GPUs, you can go buy a GPU now that has 1,024 or 2,048 cores, where each core might be relatively low performance, all things considered, but they can all run at the exact same amount of time. Okay, and so the GPUs people started using these for graphics, obviously, and then along came NVIDIA in 2007 came up with this idea of CUDA, which is basically it's an API that allows developers to run regular code, we call general purpose code, on the GPU instead of dealing with pixels. In fact, the first people that did this, they basically said, how can we convert our code into making the GPU think it's just pixels? And so they did all these conversion things and did that. And then eventually NVIDIA was like, oh, why don't we just make this a little easier? And we'll come up with an API to make it so that you can do this. And so they did this, and then now people are able to write programs that utilize all of these GPU cores. Now, part of the problem is you still have to have a very parallelizable problem to do this. It's not like they don't just, it's not like you can just say, hey, I'm doing a different thread on each core of a GPU. It's definitely more subtle than that. But if you have a good problem that is very parallelizable, you can use a GPU and get much better performance than you could using your similarly priced, anyway, CPU. And you can use multiple GPUs and so forth. So this is what happened in the late 2008, 9, or 2006, 7, 8, 9, etc. Well, one group that loved this idea were AI researchers. Okay, they realized that things like neural networks are a very parallelizable problem, and they could throw a lot of their AI and machine learning onto these GPUs and get great performance out of that. Okay, so that's kind of the how you ended up getting GPUs into the marketplace, and then AI researchers realized, hey, here's how we're going to benefit from this. And they started using a lot of GPUs for their work. Okay, well, that wasn't the end of the story. GPUs are great. They are particularly designed for pixels, although we've got APIs that allow us to use them for other things like AI and machine learning research and so forth. But of course, Google, who does a ton of AI, if you haven't figured that out, Google does a ton of AI these days, whether it's AI for learning or reading street names and any text off of Google Maps. That's a big one. I just read that they were using these tensor processing units that I'm just about to talk about for going through all of the Google Maps data and figuring out what every bit of text that came through in pictures was. So they're reading all this. And what's that good for? Doing signs. It's also good for like businesses, and it's good for like figuring out what businesses are there and what other things are there. So they did this, and they used machine learning to do this. Well, what they did, kind of in secret, the Google Brain group developed a special processor that they called a tensor processing unit. And tensors are, if you haven't taken AI, a kind of one of the data structures in a lot of machine learning algorithms. And they have this tensor processing unit that they specifically designed for the sole purpose of doing machine learning. Okay, and they announced this in 2016. They had been using it for a couple of years, kind of in secret, to kind of get the bugs out of it, I guess. And they've been using that, and then they opened it up, and now you can actually buy time on these machines, and lots of companies have kind of done this. But what is the big deal with this? Well, GPUs have thousands of cores, as we talked about. TPUs, remember, they're specifically made for AI. They have thousands of matrix multiplier units. Okay, so the matrix multiply is an algorithm that's used very extensively in a lot of machine learning type algorithms. And the original TPU, the one I put up here is like the version 3, but the original one had 256 by 256, a grid of 65,000 8-bit multipliers. Okay, and they each perform that key kind of multiplication step, and they're in a grid, and they can do this matrix multiply with them. It also had a bunch of memory. It had 24 megabytes of on-chip RAM and 4 megabytes of 32-bit registers. It's kind of a lot of registers, but they did this because they knew they were going to have a lot of data to push through this. By the way, what are the pipes in this little picture for? Any idea? Cooling, what kind of cooling?
Water.
Yeah, liquid cooling. Probably not water. Well, I doubt it's water, but probably could be. But it's liquid cooling of sorts. So the third version of this, they realized that, oh, these things are getting too hot. We're going to actually build liquid cooling straight onto them. And I'm sure the cost goes up astronomically when they do that. And kind of the last thing you want is one of those pipes to break and your liquid to like flow all over your computer. But they did that because they needed the extra energy density, and they wanted to cool it that way. So that's what they do. Remember, the more things you stick on a chip, the hotter it can get, and so that's what they needed to do for that. Okay, so what do these tensor processing units do? Now again, they are specifically designed to do neural networks, really. Okay, neural networks, if you've taken a machine learning course and talked about neural networks, they basically have 3 things you need to do. You need to do this matrix multiply. So you need to multiply a bunch of data with the weights associated with that data. And then you need to kind of add a lot of the data together to aggregate it, right? And then you apply this activation function, like a sigmoid or some other kind of function, to the data. And then you kind of do this back propagation where you kind of feed it back into the algorithm again, and then you repeat this process a number of times, and over time the algorithm ends up learning what either images or other kind of data that's similar. It learns how to use to let's say figure out what a picture is based on the fact that you've trained it with all this data. But those are the 3 things you need to do anyway. You need to multiply, you need to add, and you need to be able to use this activation function. Okay, so this is primarily matrix multiplication, at least the first 2 steps are. And therefore, having all of these 8-bit multipliers is helpful. But the question you might ask is, wait, why do we have 8-bit multipliers? That's a 1-byte number. We're not talking about like 32 or 64-bit numbers, and certainly not. And in fact, the first TPUs didn't even have floating point at all. Well, it turns out some very smart people were like, well, wait a minute, we can actually quantize this data. And what that means is we can say this 32 or 64-bit data, we can actually basically take out some information from it, but it's not going to affect the overall learning of the algorithm. So they made it so, hey, we'll change our algorithms so that we can use 8-bit data. We can kind of convert it into this 8-bit data, and therefore we can use these TPUs, which we built with the 8-bit multipliers there. Okay. The analogy that you can read the link about this, but it's kind of like if it's raining outside, you probably don't need to know how many droplets of water are falling per second. You just want to know if it's raining lightly or a heavy rainstorm or whatever. This is kind of what neural networks are able to do too. They don't necessarily need to know every little bit of data. That you can take a bunch of the information out and still get good learning performance from them. Okay, so why is this a systems thing? Well, this is all architecture, right? When it comes down to you have to make these decisions about, how are we going to build these processors? You have to make these kinds of decisions, right? I mean, remember the first time you learned about 32-bit or 64-bit might have been CS107 or something like that, right? A systems type idea when you're coming through this. So the big picture algorithms necessitate someone understanding the very low-level nature of these algorithms, such that we can build hardware to do this and build processors that will allow you to do lots and lots of these calculations very, very fast. Okay. All right. What else? So when you design hardware, okay, it's not just, hey, I've got all these multipliers, I'm going to throw them on the chip and they're going to work, right? There's a lot of other things you have to think about. Namely, if you're dealing with lots and lots of data, and Phil mentioned this earlier, that one of the reasons AI has become so important is because we have gigabytes and terabytes and petabytes of data that we can deal with. You'd better figure out how to make the memory work efficiently. Remember, memory is pretty slow, all things considered. But what you need to do is you need to figure out on this chip, where am I going to place the memory and how much memory and so forth, such that it is efficient enough to deal with this amazing amount of data that we've got flowing through the chip. So that's definitely a systems issue right there. It also turns out that the choice of instruction set is critical. Okay, so you did CS107 and you learned a little bit about the x86 instruction set and moves and adds and all those sorts of operations. And when they were building this TPU, Google had to say, hey, what kind of instruction set are we going to build for this? This actually surprised me when I started reading about it. Most computers these days have gone towards what we call the RISC design, right? Which is called the reduced instruction set computer. Your phone is a reduced instruction set computer. In fact, even your PC, although when you program it in assembly language, you use what we call a complex instruction set computer, it is actually further compiled down to a reduced instruction set computation. Correct me if I'm wrong on that, Phil. But it's actually kind of even lower than you know at this point. Yeah.
Who came up with RISC as an idea?
Yeah, who did come up with RISC as an idea? Anybody have an idea? John Hennessy, and David Patterson, and some other people, of course. Graduate students, we don't want to forget about the graduate students who had a part in this. But no, John Hennessy and David Patterson, who won the Nobel Prize a couple years ago for this, came up with this idea of, we don't need these big complex instructions, even though each instruction kind of does a lot. It's actually easier to build the hardware to be fast with fewer instructions that do less stuff. It's easier to move them around in the system and do some optimizations on that. So they came up with that, and as I said, the processor in your phone or in a Raspberry Pi uses that kind of architecture. That all the routers in here are probably a RISC-based computer as well. But TPU designers decided not to go with that methodology. They actually went with a complex instruction set computer design, mainly because multiply and add, and some other functions we'll look at in a second, are actually kind of they're the core things you need to do with this processor. And they said, well, look, if we can make the instruction set say, or when we're doing the instructions, we say, go ahead and do a multiply and add, and that turns out to be not a tiny instruction, it does more things than kind of a reduced instruction set computer instruction would do. That's actually okay because we know what we're doing with this machine. We're using it for neural networks, and we know we're going to have to do that particular thing often, and we want it to be fast, and we can optimize it for it being fast. Okay, they had about a dozen of these high-level instructions. Here's a couple of them. Read host memory. Remember we said that memory has to be really fast. Well, having the instruction finely tuned to know how to read the memory very fast is a particularly good thing. And so they built that instruction. Read the weights. Well, neural networks require weights for the nodes in them. And having an actual instruction that reads the weights, knowing that you're doing this neural network calculation, is important. Matrix multiply is one of them. And there's another one that's activate, which is for the activation function that applies a particular hard-coded activation function to your calculation. Okay? Why were they able to get away with this? Again, because they're doing a very specific design for a very specific problem, which is this training and using neural networks. So that's what we had to come out. And people who were designing this had to know a lot about, obviously, about hardware and about these big ideas, but they also had to kind of know what the AI algorithms were all about too. So there's definitely a mixing of knowledge there when they were building this. Okay. All right. If we look at what we call the floor plan of a TPU, it's actually kind of interesting. I should have another. I should have put up another one of some like a CPU to compare it against. But in here you'll notice, so the yellow in this diagram is all of the compute part of the processor, and it takes up. It looks like about a quarter of the chip is doing computations. About a quarter to probably a half of the chip is memory. Okay, which is actually, let's see. Yeah, the memory is what does it say on here? The blue is the memory, yeah. So it's about half of the data in there. We also have to do some input-output. If you have this processor actually dealing with all this data, you're going to have some logic in there to push the data on the chip and pull it off and so forth. So that's in there. And then the red is the control, which is the part of the part of the architecture that deals with the instruction decoding and instruction handling and so forth. And it turns out that's actually much less on this chip than on many other chips, particularly because they have a very, very well-defined and specific number of instructions for that. So the floor plan is kind of interesting on this when they built it. Does the TPU perform pretty well? It seems like it does. These are Google's numbers, so take them with a little bit of a grain of salt. And this is the first version of the processor. But here's how the number of predictions per second, if you're using this. If you use a regular old off-the-shelf CPU, you get about 5,000. A GPU, you get about 13,000, so it's pretty good. For the TPU, you get about 225,000. So that you could, if these numbers are true, it's probably a very good choice for neural network behavior to use a chip specifically designed for this, because it's magnitudes faster than using a CPU or a GPU. So it's probably a good idea that Google spent a lot of money they threw a lot of money at this, because look at the performance gains they got. And some smart people there had to sit down and go, should we do this idea or not? And some other people said, well, yeah, it looks like if we do it this way and this way and this way, we're going to get really great performance. And they went and did it. When you're designing chips, so I'll get to you in one second. When they're designing chips, by the way, the process is in some cases, especially at a company that has lots of money, like Google, can be very iterative. Like you try something, you send it away to get fabricated, it comes back, and then you test it, and it worked or it didn't, and then you do it again. The problem there is that it's not quick to turn things around. It's not like pushing compile and your hardware just compiles. You have to do lots of testing first, then you send it away and it gets built, and then all of a sudden you do the actual testing on it, and there's a longer window. Phil?
Yes, in the paper that Google wrote about the first TPU, which I think you bring up later.
I did bring up.
There's another interesting name in the list.
Oh, okay, great.
Yeah. Is that what they said is basically they saw that if every Android user basically needed 15 seconds of voice processed 3 times a day, it would use half of all of Google CPUs. operating at full
Yeah.
capacity. Basically, half of all of their data centers would just be processing voice, and that could
They couldn't do
that's
that.
just not cost effective. So they built the TPU in 18 months.
Yeah,
Because
yeah.
otherwise the world
So-
was going to end.
Right. Right. So when you say, "Hey Google, is it raining outside or whatever?" Right? That has to go to some server at Google and get processed, and it has to do the natural language processing to figure that out. And as Phil said, Google made a calculation and said, "There's a lot of Android phones out there, and if everybody wants to ask a question, we're not going to have enough processing to do this. It's just not going to work." So then they went and created these TPUs to handle a lot of that. So yeah, I mean, a lot of these great innovations come from business decisions or seeing what's really happening in the world. And up until recently, we didn't have enough scale on computing to need to worry about these things, right? It wasn't that a billion people had Android phones in the world, right? Now they do. So that's kind of important. Why are these TPUs so much faster and so much better? Well, because they were specifically designed to do exactly what the problem was. Right? They are specifically designed with neural network calculations in mind. This instruction set was a correctly chosen instruction set, or at least a good one, because it seems to have worked. The fact that you can quantize all of the data and you can do integer math on it, and the neural networks still actually work just fine, etc., is the reason that these are so much better than off-the-shelf other types of components, right? So, one other thing, Google's made them a little bit better so that they can work together. Okay, Google has these data centers, and it's not like you have one TPU on its own now, working, kind of chugging away doing these calculations. You can put them together in what they're calling pods, which you put in a data center, and they work together and kind of multiply the effect of the speed at which they can do the calculations to solve bigger and bigger problems. This again is Google numbers here, but they say that if you have a pod of these TPU, version 3 TPUs, they can work at what we call 100 plus petaflops. Okay, who's heard of a flop or flops before? A few people? Yeah. Flop is a floating operation per second. Flops are floating operations per second, and it's kind of a wonky metric, but it basically means how many math calculations can you do a second with your processor for a given problem. 100 plus petaflops is an incredible number, especially for something that fits in a data center or fits on in a rack of computers. For example, your laptop is in the tens of gigaflops, right? Which is actually pretty impressive too. I mean, I remember back in this is going to date me, but back in like the 80s, there was a supercomputer called the Cray supercomputer, and it was talking about working on a megaflop and 1 million floating operations per second. And that was like incredible in those kind of days. But the laptop on your desk or the phone in your pocket works in the gigaflop sort of range. But the 100 petaflops is like 10 million times that as fast as your laptop in that case. So super duper fast. And so now Google can throw a lot of data at this, like when you ask your phone something and it can instantly come back with a response because it's particularly fast. So the TPU is that much faster than your laptop, but it can't browse Reddit. Right? I mean, the TPU is not meant for general purpose calculations. Like you can't say, oh great, when am I going to get my next MacBook that has a TPU as its main processor? It's not going to happen because it's only built to really do neural network calculations, and that's not going to happen anytime soon. Okay, so that's a TPU, which I think is an interesting bit of hardware that many of you will either use or you'll use other sorts of hardware that's kind of designed for this. If you end up in AI, you will probably use similar sorts of things, whether you know it or not. And that's kind of the one point here, is that you don't necessarily need to understand all of the systems level things for this, but hopefully you'll have some appreciation for the fact that all of this great AI and machine learning that you're doing relies on people who are building this kind of hardware. Okay, So while we're talking about Google, I thought I'd mention the TensorFlow framework, and Google had actually designed, I believe TensorFlow was before the TPU. They designed this framework at open source library, which is nice. That's a machine learning framework that works on tons of different platforms. You can use it on your Mac or on your Windows PC or your phone even. In fact, there's a JavaScript version which kind of I think is a little, it seems ludicrous to me that is actually a thing, because it seems like it would not be particularly speedy, but I don't know what parts of it are like literally in your browser. But you can use them on many different devices, many different operating systems, and it's written in Python, C++, and then CUDA, because they're utilizing these NVIDIA GPUs. And in fact, other languages too. I went and looked up because it's open source, you can go look at the actual code for TensorFlow. And you can see that just if you look at the folder listed on the main TensorFlow page here, on GitHub, there's all the folders. Well, there's a C folder, and there's a C++ folder. There's a compiler folder, because there's got to do the compiling for this program. There's a Go folder. Google has invented this language called Go. If you haven't, it's another kind of systems-y kind of language. There's a Java folder. There's a JavaScript folder. There's a Python folder. I mean, if you're working on TensorFlow, you probably have to know a lot about systems things and a lot about different languages and so forth, although you may be on just one particular part of it. There's a lot that goes into a machine learning framework that's this large. Phil has mentioned this before, that the lead of Google AI is a guy named Jeff Dean, who he talked about in the MapReduce paper. He's one of the authors on the MapReduce paper, and he's a systems person. Like, he got his training in systems, now works in AI, and is responsible for a lot of these big algorithms that have been used, like MapReduce, and he's part of the team that's played a big part in TensorFlow, and he's a systems guy. So there you go. In fact, the TensorFlow paper, I highlighted Jeff Dean in this paper. One thing to note about the paper they wrote about TensorFlow, there are like 40 people on this, right? If you create a big, giant system for something, or a framework or whatever, you're going to have a lot of people contributing to it, and they've tried to give as many people as they could credit, I'm sure, but it seems a little crazy to see a paper with 40 people on it, but that's the way things are kind of going these days. The days of doing independent, on your own, yourself research are kind of going away for these big giant projects. And Phil, you were going to mention somebody else I should look for on this.
Oh, I was just saying the tensor processing unit.
Oh, is that on a different one?
Yeah.
Oh, sorry, I thought it was this one.
It's David Patterson.
Oh, it's David Patterson on that.
Patterson actually helped design the TPU, and my guess is John Hennessy makes fun of him that he designed a CISC.
Yeah, that's probably true. Yeah. So TensorFlow is now, Google built the TPUs so they could do TensorFlow, right? That was kind of, again, they've got this great API, and they go, oh, we're doing it on all these GPUs, and it's not fast enough. Let's go build a specific piece of hardware to do this. They told the Google Brain folks to go and put their heads together and do this, and next thing you know, you've got TPUs, and they're super duper fast for neural networks and machine learning. And by the way, Google hasn't been shy about selling this technology to lots of other companies either. So this is a good thing about a company like Google coming and doing this. They could have kept it all to themselves, but they've decided to make some money on it by selling the technology to lots of other companies. So if you go look at the main TensorFlow page, they list like hundreds of companies that are using TPUs now to do machine learning.
Yeah, and I think I mentioned this with MapReduce. So I was chatting with some folks at Google, and one of the reasons why they open sourced all of this was they wrote the MapReduce paper, and everybody thought it was amazing, but it was just a secret Google system. So then Apache wrote Hadoop, and comparatively Hadoop was terrible, 10 times slower. And it's sort of this canonical example of like system software that's kind of bad. And Google, basically it was this problem, like everybody wanted to use it, but then there was just a bad implementation, and it kind of made it not, you're just wasting huge numbers of cycles to try and do large-scale data processing. And so then for TensorFlow, they wanted to release it so that people would have efficient stuff, so you're not using up 90% of your energy putting carbon dioxide in the air for bad reasons.
Yeah, so right. As Phil said, that they said, well, this is a great idea. Let's not let's not make somebody else try to come up with it and do it poorly. And so that's it. I also think it's because they make a lot of money off it. That's probably true too, or at least some money off it. But that's TensorFlow. So that's kind of the Google side of what's happening in AI right now. I thought I'd talk about a couple other pieces of the puzzle, or things that are happening in systems that you may have heard of or used before. Let's go over to another giant tech company, Amazon. Amazon has this a couple different systems. We're going to talk about both of them. They have this system called Elastic Cloud Compute, otherwise known as EC2. And if you want to run a server, how do you do it, right? If you want to run a server, what do? You could go and buy a computer, and you might want to buy a fast one, and if you think your website or whatever you're going to build on this server is going to be popular. And you could hook it up, and generally you have to pay somebody, you have to pay like a hosting service to actually like have it at their data center or whatever so that it can get high bandwidth connections and so forth. You can't really run a very good server out of your house. Comcast really doesn't want you to do it either, but you could, but it's not going to be particularly fast. But you would still have to manage it yourself, and you'd have to have all the software on it, and you'd have to do all that. And that's probably not something you want to do if you've got this great website idea. You want to just build your website and let somebody else handle that. So what you can do is you can call up a hosting company and go, hey, can I rent a server from you? And if you manage all the software, you just let me put my website on it. And that's great. These were kind of the options you had for a little while. Let's say you went and set up a website, thecutestkittenpics.com, and it turns out to be a hit, and it's huge, and like millions of people are going to that server every day, going to your website to like buy kitten t-shirts or whatever. If you're doing that, if you have one computer trying to handle millions of requests, you're quickly going to run out of, you're not going to be able to accept those requests, no matter how many threads you have, right? Or how big your thread pool is. You're just not going to be able to do that with one computer. So what you want is you want to just spread the load over multiple computers. So what would you have to do? You have to buy another computer, or you have to buy many computers, 5 or 10, or however many you think will scale up to the amount of traffic you want. Or you rent more computers from the hosting company, but this is going to take a little time to do. You got to call up the hosting company and go, hey, can I have 5 more servers? Or you're going to say, you know, can I need to purchase these, here I'm going to ship them to you or whatever. In the meantime, you're losing all this money because people can't buy your t-shirts, right? They're getting, can't go to the website, you know, denied, whatever. And that's not true. So that was the option, basically, until Amazon came along and launched the Elastic Cloud Compute. So I'd say compute, not computer, service around 2006. The way I understand it, and Phil, if you know more details about this, let me know. Amazon realized that they would have to buy tons of computing for their own use because Amazon was growing really big. And so they bought a lot of computers, and then they realized, actually, we're not going to really need to use all these quite yet. Like, we're not going to use them, but we're still going to buy more, whatever. Let's open this up and let other people use them. Why not? There's probably a big use for this. And so they did. They allowed people to use this service. And what it was virtual machines, kind of like VMware. They use a slightly different. They use a different VM for it called Zen, or at least they did. They probably use different ones now. But they allowed you to basically spin up as many of these virtual servers as you want, and they will do it automatically when traffic to your website gets too big and so forth. And they kind of automated this process, and that was the elastic part of it. They say, hey, you can buy this service from us, and if you all of a sudden get, you know, your kitten website takes off, we will scale it more or less for you, and we'll charge you for it, but we'll scale it for you, and it will be able to handle the extra traffic, right? And if like your kitten website's a fad and next week all the traffic drops off, then it just scales back to whatever you need. So this was a big, kind of a cool new way of doing scaling your website, or scaling your online kind of presence if you wanted to. It wasn't just, you know, Chris Gregg with his kitten website though. Turns out there's lots of, I guess that's the next slide. Where'd it go? Oh no, there it is. Yeah, it is on the slide. I had it in a different form. Lots of different companies actually use EC2 now, companies that you might think, wait, they don't have their own stuff? NASA, right? NASA uses EC2 to do its servers. Netflix right? Netflix is a company that I would have, if you had asked me, I would have bet the farm that they had their own servers for everything they did. But they realized, wait a minute, Amazon's already doing this. We can scale everything we need through Amazon. Why don't we just pay them to do it? And they did. And it turned out to work fine, right? Slack, Adobe, all these big companies, Reddit, all hosted on EC2 servers. And these are like companies that and websites that have tons of traffic. And Amazon's like, yep, we'll buy more computers and set them up and have it all working efficiently. Okay, what is the systems kind of challenge to hosting something like this? Well, first of all, you have to deal with all the infrastructure. Amazon has millions and millions of CPUs and data centers that are doing EC2 servers. They have to deal with the security for that. Right? You don't want to rent a server from Amazon and then all of a sudden have it easy to break into. One of the biggest problems, by the way, is that people are keeping their private keys in their GitHub repositories. Right? You'd be like, oh, it's got to log on, so I'm going to keep it in there. Don't do that, because people scrape GitHub and find your keys and then do their own computing for like Bitcoin mining and whatever. But they have to handle the security part of that. They obviously have to handle the software. Most of it is Linux-based. You can get Windows servers through EC2 if you want to. They have to handle the storage. We'll talk a little bit more about storage in a minute, but think about how much data Netflix actually has to store, right? It's a lot, and you have to handle that sort of thing. They have to make it reliable. That's the other thing. I mean, how often does Netflix like go down hard? Occasionally, right? Like once every couple months, I'll be like, wait, why isn't Netflix working? Right? But that's pretty rare, all things considered, especially for something that's serving billions or hundreds of millions of people. They also have to handle, of course, the IP addresses and all the networking that goes along with that. So that's a big systems issue there. When you get a VM on EC2, you have sudo access to it. You can go and do rm/r star if you want to, and it will erase everything on there, and it'll crash and whatever, but you spin up another one, and that's the way it goes. But they want you to have access to it so that you can do whatever you need to with it. So you can do that. Now, they keep the virtual machines separate in such a way that's secure. You can't access somebody else's and so forth. You can also, they also have GPU machines you can use for your EC2 computing needs if you want to, if you have things that you need to do on that. They offer another service called the Lambda service, which is basically a serverless compute. They're like, you don't even need to have a server with us. You just send us your code in a particular form and so forth, and we'll run it for you, and then give you back the results. That's kind of nice too if you happen to have problems that you need. I need to run this, but I don't want to bother with the servers. So they will do that. So that's EC2. Another kind of giant like thing that's available out there for you. And you can do that. Google has like Google Compute Credits and so forth. They also do something similar to that. But Amazon's kind of the leader in terms of if you want to go get service, go for it. You can go and purchase it. And by the way, it's pretty cheap for like students and things, right? So it's actually easy you can get some free versions of this even to test out if you want to. So pretty cool. What other thing does Amazon have? Well, as I said, they have to do a lot of storage. So Amazon has this thing called the Simple Storage Service, S3, which is basically a big place to store all your data. And you can store as much of it as you want. You'll pay for it, but you'll store as much of it as you want. And what does it offer? It offers scalable storage. If you're trying to store a megabyte, great. If you're trying to store terabytes and terabytes of data, they will gladly store it for you, right? For a cost, of course. There's also backup and recovery. It's very nice to know that when you put your data up onto the S3 service, it's probably going to be okay. They duplicate it, they use RAID, they farm it out to different data centers around the world. So if there's like some volcano in Nevada where one of their data centers is, or some earthquake or something, and that destroys their data center, your data is probably also in Ireland or somewhere else in the world, and it will be fine. So they offer the backup and the recovery of your data. Disaster recovery, like if your entire data kind of disappears from there, so they'll recover it from some other server that they have. Data archives. There are lots of places that need to archive a lot of data. A good example for that is CERN and the Hadron Collider. they are collecting like petabytes of data at that thing. They need to store a lot of that data. I'm not sure if they use S3, but they could, right, if they wanted to store all the data, because it's very good. They also allow things, I had to look up this term, but there's a thing called data lakes for analytics, which is basically you have all your raw data. What are you going to do with it? Instead of trying to put it into some format, you just go like, look, we're just going to throw it up there, deal with it when we need to. They offer that. What does Amazon do with, what else do they say is so great about their service? Scalable. Again, you can put 1 megabyte or 10 terabytes, and they'll just take all your data and store it. It's got very high availability, which is great. 99.99% uptime, which actually seems like a lot, but that's 43 minutes a month where they say, no, you're not going to get your data. Some people might not like that so much, but maybe you got to go to a different way of doing it. But it has pretty low latency. In other words, getting a piece of your data should be very fast, and they offer that. And here's the big one: they offer 99 point lots of nines durability, meaning that if you give them your data, they will not lose it and they will not destroy it. It will be available to you, and that's for some people, that's key to the entire thing. They're like, I don't really care if I can get my data instantly, but as long as I can get it, that's the benefit, right? You're going to store it, and unless there's like World War III or whatever, it's probably going to be okay, and your data won't be destroyed. So that's it. Now, all of these things, you have to have a pretty well-oiled system to be able to tout these and guarantee the things that they can guarantee. Trust me, Amazon has lots and lots of systems people and IT people who keep these things running smoothly and are always innovating to like, how can we do it better, and how can our data centers be more efficient? And by the way, we have to put our data centers somewhere where there's lots of solar power, because that's actually going to be cheaper in the long run than trying to go to places where there's coal power or some other type of power. And so data center designers think about these things as well. So that's Amazon. Okay. I thought we'd talk a little bit about the internet backbone. I have a question. Who owns the internet? What? No one owns the internet. Yeah, no one owns the internet. I mean, obviously that's kind of a silly question, but lots of companies, and it's mainly companies as it turns out, own the data lines that connect and own the routers that connect kind of the big parts of the internet together. Right? I mean, Stanford, we have a lot of servers here, and we have a big network on the campus here. But if we want to talk to Berkeley or whatever, or if we want to talk to somebody across the country, MIT, the data has to go through a whole number of jumps, like we saw with Traceroute, to get there. And the question is, who actually owns those things? Well, it turns out a bunch of companies own that, what we call the backbone. It's a little bit nebulous as to exactly where those lines are and who actually owns some of them and how they're working. This little picture here, this diagram here, is a map that was done by a group at University of Wisconsin, where they were trying to figure out like where are all these kind of main network internet hubs in the United States, and it took them 4 years to put this diagram together. Like it's not like you can just look it up and go, hey, where's all of AT&T's routers? They don't publish that sort of thing. They don't publish it for a couple of reasons, by the way. Number one, it's proprietary and they own it, and why do they need to tell you where it is? But number two, it's for security reasons, right? The network, the backbone of the internet, if you can take that down, if you're a terrorist or you're doing malicious things, probably a good place to start, right? And so they keep those a little bit secret. That might be a little concerning to some people too. Like if you say, I kind of want to know where my internet routers are, and nobody will tell you, that might be a little concerning, because who knows what they're doing there and so forth. And in fact, if you go look up AT&T NSA, you'll find lots of things about where AT&T is using their data centers to collect a lot of data that you may not agree that you'd want collected, for instance. So anyway, that's that. Now, why is it AT&T and Verizon and some of these other big companies, Level 3 is another one, and why are those the companies that own this? Well, because they own the telephone lines, and it turns out that many of the networks, at least originally, started by going on the same path as all the telephone lines. So a lot of these big companies that were telephone companies got into the internet game at that point and have continued in that business. Okay, that's how that works. How does it actually work if AT&T owns some of the things and like Sprint owns some others and Verizon owns some others? How do they actually pay for each other's traffic? Well, they actually keep these things called peerless agreements between various groups. And many times those are, you let me use yours, I'll let you use my data, my internet routers and so forth, and no charge. We'll just know that we can each use each other's. And so a lot of times it's a free agreement, which is why it tends to work fairly well. It doesn't always work well. Netflix comes along and pays this company Level 3 to use their services, and Level 3 goes to AT&T, goes, hey, we've got this agreement here, I'm going to dump you trillions of bytes of Netflix data, and AT&T's like, well, wait a minute, I want a piece of this too. It's not even. I'm not giving back enough data. And so there were issues with that. Comcast ran into issues with that where they were trying to charge Netflix and so forth. If you want a really good read, start reading about net neutrality and seeing how that may pan out in the next few years. It's been kind of big and small in the news. It's a big deal sometimes, but then it kind of gets pushed under the rug when other big news items come about, and it's pretty important. Like your data may not be the same model going forward, but that's that. What else about the internet backbone? It has to be pretty fast. There is a lot of data going along here. These fiber links, if you have one strand of a fiber link, it can be up to 100 gigabits per second along that link. And that's pretty fast, right? 100 gigabits per second. Your wired connection, if you're in a dorm, you have a wired connection, that could be up to 1 gigabit per second. It's pretty fast, but that's most you're going to get in your own computer. Wi-Fi is capped at, if you're really, really lucky and you're on a good 5 gigahertz network, you might get 450 megabits per second, although I've never seen it. But you might get up to that. But those are the kind of numbers we're talking about for individuals. It has to be pretty secure, obviously, as I said. It's a good candidate for targeting if you're trying to do malicious things. Some countries keep close control over their inbound and outbound connections. If you remember the Arab Spring from a number of years ago, Egypt cut off internet access outside the country. They just said, nope, no more internet access. We want to handle, we don't want people to be able to talk to other things. And they did that for 5 days. And that was kind of a big deal that they could do that. Countries like China, for instance, have proxy servers that are very controlling over these things, and they control all inbound and outbound traffic. And so it can get a little scary sometimes, and countries do it for a reason too. But just have to know that sort of thing happens when companies and countries can control these things. There's lots of system challenges that go into the backbone, right? Not just the fact that you've got to string all these long cables and you have to have thousands of routers and so forth. I still don't know, maybe Phil knows, how does an individual computer handle a 100 gigabit per second connection? I don't think the computer's fast enough.
Custom hardware.
Yeah, it is custom hardware. I did a little calculation. I hope the calculation is right. But if you have 100 gigabits per second, that means you have to do 1 byte every 8 times 10 to the negative 11th seconds, which is every 8 picoseconds. That would be really hard to do on your CPU. In fact, impossible. Your CPU runs at let's say 1 or 2 or 3 gigahertz, which means it can do 1 or 2 or 3 giga things per second. And if you're trying to do 1 every 8 picoseconds, that's too fast. Your computer cannot do it that fast. So there's got to be a lot of custom hardware, and they have to do that. So lots of systems challenges there. Okay, so that's the internet backbone. The last thing I wanted to kind of mention briefly is there's a lot of systems programming that goes on for your entertainment, right? If you look at Pixar, for instance, right? Pixar is in the business of making animation that's computerized. And when Toy Story came out, which was 1995, which is a while ago at this point, they said that Pixar had 117 computers, which today seems ludicrously small. But they had 117 computers running 24 hours a day just to render this movie. Okay, and it said that Each frame in the movie, and there were 114,000 of them, each frame took between 45 minutes and 30 hours, depending on what was going on in that frame, to render. Right? Well, in order to do that, they had to have some pretty specialized hardware. Okay, number one, we've already talked about this in other contexts, but if you're running a program, if you're running a particular algorithm for 30 hours, there is a non-zero chance that the computer will crash. And you have to redo either part of that or the entire calculation. And if you've got a system where you have to redo the entire calculation, it's probably not a good thing because you will never be able to finish because of the amount of times computers just act like really crash or hard drives crash and so forth. So part of Pixar's success was fight the systems battle to make these computers do their things as fast as they can. They needed the computers to run efficiently. They needed networks to connect them. They needed storage. They needed tons. Then in 1995, they had like terabytes of storage, and this was like people didn't even know what the terabyte meant in 1995. It was like so much, right? These days you've got it in your computer, but that was it. And they had to have good software, which took systems level programming to do. In particular, Professor Pat Hanrahan, who's a professor here in this computer science department, was one of the creators of this software called RenderMan, which handled a lot of this. And trust me, Pat Hanrahan's pretty good at systems. Right? Why? Because he needed to do a lot of this in order to make this stuff work so that we could have computerized animation. Yeah.
So Pat's first job when he joined Pixar, because he has a PhD in, I think it's biophysics, was to fix the makes files.
Yeah, fix the makes file, yeah.
That was his job, was fixing the make files.
Yep. Yeah, he said, I remember hearing him talk about this where he said, I sat down and I typed make, and it was just a string of errors or whatever. Nothing worked, and it took him weeks or something to figure out what was wrong with these make files. But yeah, so there's a lot of systems that goes into creating things that come from entertainment. And of course, animation hasn't just stayed at that level. It's not like they can use one computer these days and knock out an entire Pixar movie. Toy Story 4. Which I guess just came out recently, is it about to come out or did it come out? But anyway, it still can take 60 to 160 hours to render one frame. Why? Because now they need the hair to wave exactly like it would on a real person, right? And they want to make it exactly, and so they're adding so much more detail to it that it still takes a lot of time, even though they now use data centers and so forth to do a lot of processing.
Yes, I worked with Disney a little while ago, and it turns out they have one of the top 100 supercomputers.
Yeah, Disney has one of the top 100
Frozen
supercomputers.
or Wreck-It Ralph or something like that.
Yeah.
It's like the next time you see Wreck-It Ralph, Ralph Breaks the Internet, when they first see the internet and you just see how big and complicated that scene is and they're rendering it, it's pretty staggering.
It's pretty staggering, yeah. Yeah, and big companies that want to do this sort of thing need to spend lots and lots of money on both computers and computing power and the engineers and the systems engineers to actually build the tools and software and hardware, put it all together to make it work. 3D games or any computer kind of animation these days have become so complex that you really need to do low-level coding to make them work and to get the game engines to work and so forth. It's no secret that if you're going into game design, you better know C++, because most games these days are written in C++ because they need access to be able to do low-level, very fast computing, and that's to get 60 frames per second. You need that. Virtual reality is another one. Trust me, if you're working in a virtual reality company, they're going to have lots of people who do lots of system stuff, just because they're going to need the hardware to work well with the equipment and make it so that it works efficiently. And then, of course, designers for hardware consoles. That's a lot of systems work. I remember when I think it was the PlayStation 2 came out. It was a very parallel computer, much like it was kind of similar to a GPU system, although it was CPUs. Do you remember the name? The Cell architecture. That's what it was. Where it was a specific design because they went, wait, we need to play these games fast. What's the best system we can use? We can't use a regular old PC. It's not going to be fast enough. And so they had this other cell-based cell computer to do that, and it worked great. They had very fast processing for PlayStation 2. So that's that. So here's a couple final thoughts on this. although you've spent a lot of time doing projects that you're like, I don't really ever want to look at a proxy server again. I understand that. You've learned a lot of things that that will hopefully give you some insight into the fact that it takes a lot of systems coding to make the things that you probably may go and work on work, right? Whether it's from just browsing the internet to email to doing AI, machine learning, et cetera, that's going on at these tech companies, there's got to be a lot of systems even today that goes into doing that. You may be kind of 4 levels above some of that stuff, but having an understanding of that to know that when your boss comes and says, hey, I need to get this done in 2 hours, you go, look, we just don't have the compute resources to do that. We need to go buy a bunch of other servers or whatever. Then that's the insight that will hopefully help you out. If the systems goes wrong, it can be devastating, right? There was a computer in the mid-90s called the Itanium, which is an Intel computer chip design, and they built it, and they had all these great ideas for it, and it was going to be this super fast computer, and it turns out it was too hot and didn't run well, and very few people use them even today, and it was kind of a flop because they just didn't do the right programming for it, and the design of the hardware wasn't that good, and this was just at the cusp of kind of multi-core coming online as well. So it's devastating when your systems systems coding and hardware design and so forth doesn't work. And of course it's evolving all the time, right? The types of systems work that was going on 30 years ago is similar, but certainly much more evolved than this, or today it's much more evolved than what was going on then. And if you're in systems, you got to kind of follow along with the current technology and keep up. Quantum computing, for instance, is going to be coming along, at least we think it is, it may be mainstream in a decade or so, or 2 or whatever. Guess what? There's going to be a lot of system programming challenges that go along with trying to make those computers do things efficiently and fast. So you may or may not stick with systems and do more systems class. Maybe the last systems class you take. If it is, we're glad to have had you here. Hopefully you learned a lot from it and you made it through. And if you do end up in more systems, great. We talked about lots of different systems classes that can come up in the future, and you can think about that. But if you don't, hopefully you have an appreciation for the worth of it and what goes into some of these big projects and big computing systems, and hopefully that appreciation will kind of carry with you in your future jobs. That is all I have for the class. Phil, any other last words? No? Okay, we will see you in the final exam a week from Friday, and thanks for being part of 110. We'll see you later. Thank you.